We now look at the dynamic program to find the optimal well-behaved tour within good running time. And the dynamic program we will do in 3 steps. The first step, we'll now look at one specific square of the dissection. So if I take an optimal well-behaved tour, how does this look like locally in this square? There is still stuff outside, so it doesn't have to be a cycle in here. But it is a cover of all the houses in the square by paths. So here we have 4 paths, the green one, the blue one, the brown and the cyan one. And each of these paths starts in some portal and ends in some portal and picks a few of the houses on the way. In the global solution, it might look like that this path continues somewhere and then comes back to the blue one. Then we go through here, we continue somewhere, come back here, we go through this, continue somewhere, come back here, go through this. But locally, we only have these paths. And since this collects all the houses, this is called a path cover. We cover all the houses with paths from a portal to another portal. But not any path cover is valid. We had the restriction that every portal is visited at most twice. So of course we can only consider path covers where the portals are visited at most twice. In this example, these are visited once, this is visited twice, all the other portals are visited 0 times. So if I just want to guess, how often do I visit every portal? That still doesn't tell me in which order we visit them. So this doesn't tell me that the green path starts here and ends there. It just tells me there is some path that starts here and there are 2 paths that start or end here. How many possibilities are there? How many combinations can we get? Well, we know from earlier the number of portals we have at the square is at most 4 to the m. For each portal, it can be visited 0 times, once or twice. So there are 3 possibilities for every portal. That means we have at most 3 to the 4m combinations of 0s, 1s and 2s we can place here. And the m, that's in order of log n divided by epsilon. So if we plug that in here, we have 3 to the order of log n divided by epsilon. And then again, use the logarithm rules here, we get n to the order of 1 over epsilon possibilities. And this is polynomial in n, so that's fine for us. So we can guess how often is every portal chosen, and we try all the possibilities of this and find for each of those combinations the best well-behaved tour. But we still don't know in which order they are visited. So we still have to figure out, do I combine this portal with this one, or with this one, or with this one? That gives us even more combinations that we have to consider. And those are the crossing-free pairings of the visited portals. So here we have these pairings, and this is fine. So if I take all these portals in the order that they appear on the boundary, I can lay them out linearly. And then only look at these pairings like brackets. So this is fine. I can visit the blue ones, and then outside we have the green. That is okay. But this is not fine. I cannot go from a blue to another blue, and then in between we have a green one. That here would mean that we start in this and end in this with one path, and start in this and end with this with another one. Then we have a crossing. So we have to figure out how many of these possibilities do we get. So the number of crossing-free pairings of visited portals in total is the number of visit vectors, so the 0, 1s and 2s we can place there, and for each of them the number of realizing pairings. This we know, that's n to the order of 1 over epsilon. But how many pairings are realizing now for this visit vectors? How many can we find that are valid? Well, this is just number of ways we can use brackets in a word. Or it is the number of different trees you can have. And that one is very well studied. That's 2 to the order of number of vertices you have. we have order of m vertices, so the number of crossing free pairings we have here is 2 to the order of m. If we want to be precise, then we get the exact number of pairings from the Catalan numbers. So if you want to figure out how exactly to get this number, just look for Catalan numbers, then you find a lot of stuff in Google and even on Wikipedia that helps you understand it, but that takes too long to cover it here in the lecture. I just take it as a given. We have at most 2 to the order of m realizing pairings here. And this is again order of log n over epsilon. We use the logarithm rules, we get again n to the order of 1 over epsilon, so we have in total n to the order of 1 over epsilon. Why is it the same if we multiply it? Because it just gives me a factor 2 in this order. If I have n to the k and I multiply it with n to the k, then this is n to the k squared. You can pull the 2 in, then you have n to the 2k. So the factor 2 just disappears in this Landau symbol. And we are still somewhere in the order of 1 over epsilon, some constant divided by epsilon. So this is the total number of crossing free pairings that we can have. So now what we want to do is just brute force. We take a square in the dissection and we take any crossing free pairing, and then for this we compute the optimal path cover that respects p. And we do that for all the n to the order of 1 over epsilon crossing free pairings. So the time we take for that is this much times however much we take to compute this optimal path cover. So now for a single one, how do we do this? So we know which portals are visited and in which order. So we know exactly there is one path that starts here and ends here, one that starts here and ends here. We have our crossing free pairing given. And for this we want to find the optimal path cover. How does that work? And for that we have to use the recursion. We have to further dissect it into smaller ones. And we assume that for all the smaller squares, we already found the optimal solution for every crossing free pairing we have there. So we dissect it even more. And now we have these 4 squares. And for these 4 squares, we know for every crossing free pairing inside here, what's the optimal tour we can get. So we picked our crossing free pairing for the large square. And now we only have to find the best solutions of these squares that respect this pairing and that can be combined. Well, I said only, but how many of these are there still? If I just look at this square here, I mean the top side is fixed, the left side is fixed, but at the bottom and right we have no clue. So we still have to guess here what happens on the right side, how many portals do we visit, which portals do we visit, and how are they paired, and the same here with the left and the bottom side. How many of these combinations do we have? Well, for each square we have n to the order of 1 over epsilon crossing free pairings in total. So the number of pairings that respect this choice is of course not more, so we have here n to the order of 1 over epsilon. And we have 4 of these squares that we have to combine, so we have to take this whole thing to the power of 4. But now the 4 again gets lost inside the Landau symbol. This is just another constant that we have here. So this shows us the power of having our own notation in the exponent. We can just take whatever we have, take it to the power of some constant, and it's still the same because it's just another constant we have to add here to the exponent, so we don't care about it. As long as we only have the asymptotic behavior here in the exponent, it's all okay. So we still have only n to the order of 1 over epsilon crossing free pairings of the child squares that we have to combine. So we calculate all crossing free pairings here, all here, all here, all here, figure out if they can be plugged in together. For example, this one here works, they can be combined, and then find that one that gives us the minimum length. So the one with the minimum cost over all that respect p. And the respect p means that if I take this brown one here and I follow the path through the smaller ones, then I end up at the correct one. So this is a tour that respects our p. What about this one? Is this valid? No, it's not, because the green and the blue and the brown, they start in the correct one, but they don't end in the correct one. The blue one goes here, that's not a fine. What about this? Is this valid? Also not, because there's no path that connects these two vertices here, but they have to be paired because of the green pairing, so this is also not fine. What about this? Is this valid? No, also not, because we have this path inside here, and that's not something we're allowed to have. All the paths we have, they have to start in some of these portals of the outside square. This is also not one that respects p. What about this? Is this fine? Yes, this is fine. Here everything works out. We have connected the correct vertices, we don't have any crossings, we don't have any paths or cycles that shouldn't be there. This is finally a choice that respects p. And this is one we would consider and then find the minimum over all of those. And proving that this gives us a correct solution, that we can do by induction. I won't go into details here, but the idea is basically assume that you've correctly computed everything for the smaller square. That we can assume because in the base case we only have a square of size 1 and then it's very easy to brute force compute everything. Then do we find the minimum here? Well, we have looked at all the possibilities that things can be combined, so of course the minimum has to be in there. And then that way you can quickly show that for the next square you also get the minimum, provided that you had the minimum before, and then you get the correctness. And this gives us the lemma. We can find the optimal well-behaved tour in n to the order of 1 over epsilon time.